Hi everyone. This lesson, lesson 2.2, builds on what we did in the first lesson of this unit, which was talk about exponents. So in this, we're going to talk about two things, radicals and fractional exponents. So radicals sounds like a somewhat intimidating term when you think about it, but basically, when you have two or more equal factors, in this case, let's say you have 5 times 5. So you can express that as 5 to the exponent 2. And if you multiply that out, you get 25. So all of you have seen the term or heard the term the square root or the root of a function. So what that means is if you look, what the square root is or what the root is you're finding a number that when you multiply it together a certain number of times, in this case, if you find the square root, you have the number 5 multiplied by itself twice, so 5 times 5 gives you a number 25. What that means is the number 5 is the square root of 25. Okay? So 5 would be known as the root, and 2 is known as the power of the root. So if it's 2, it means it's the second order root. If you look at some additional examples, if we have 2 times 2 times 2, okay, you can also write that as 2 to the exponent 3, as we talked about in the last lesson. And that is equal to 8, right? If you were to multiply that out in your calculator. So what this means is 2 is a third order root of 8, okay? So if you were to write that, you see the root sign, okay? And you'd write the number of the root, okay, on this little kind of V-shaped piece above the side of the root sign. So you'd write a 3 there. And what it means by third order root is that whatever that number is, 2 times 2 times 2 in this case is 8. If you have the number 81, we say 3 is a fourth order root of 81. Okay, again, you can see how I've written it here with the 4 here in the root sign. And what that means is whatever number comes out here, that number multiplied by itself, in this case 4 times, would equal 81, or the number that's under this root sign here. Okay? If you want to talk about it in algebraic terms, okay, if you have b to the exponent 5, then b is the fifth order root of b to the exponent 5. Or again, writing it with the root form, you have the root sign with 5, and it's of b to the exponent 5 is just equal to b. Okay? So the symbol that you saw used there was the root sign. Okay? Oftentimes, you'll see that sign on your calculator, and you'll see usually a couple options. The root sign, which that is just the square root. Okay, we'll talk about that in a second. Oftentimes you'll see another button for the cube root or the third order root. Okay, so it has the number 3. And then you'll see another button with just an X here. And what that means is you tell it what order root it is. Okay, so if you have a second or a third order root, you'd oftentimes use these buttons. But if you have a fourth or a fifth order root, you would use this button here, and you would tell your calculator what order it is. Okay, so fifth order, whatever that number may be. Okay. With a root sign, you're always, if you want to find the negative root of something, okay, specifically with square roots, you have to place a negative before it, but we'll talk about that in specific examples. Okay, so as I mentioned in the last slide, and as I talked about with these buttons here, the order of the root is written in the upper left-hand corner. Okay, so kind of above where this little V shape is. Okay, the exception to that is when you have a square root. Okay, so on your calculator, you'll see a square root symbol, and more often than not, it just looks like this. Okay, so it doesn't have the number 2. And that's just like when we talked about exponents. Okay, when we talked about the number 6, let's say, and that's actually 6 to the exponent 1. The same kind of convention applies for the square root. Okay, if you just see a symbol with the square root sign, just like this here, without the 2, it's implied that that's the square root, and that's just because it's normal convention. Okay? So this expression, we talked about the term, I mentioned the term radical. So these types of numbers with a root sign are called radical numbers. Okay? That is what you're going to think of every time you think of a radical number, something with a root sign. All right? The order of the root is listed, okay, again in that top left corner. That's called the index. And the number under the root sign, in this case, the number 32, that actually has a fancy term. Okay, it's known as the radicand. I'm not expecting you to memorize those terms. I'm just explaining what I'm going to call the fancy terms are for each one of these. Okay? So let's look at a few examples. Okay, this is intended to be done without a calculator. So if we were doing this in an in-person class, I would have you calculate these without a calculator. Since we're doing it by video, what I recommend is you could have paused it already and tried them, or pause it after I finish my monologue right now. And try these without a calculator. Okay, these should be ones that you can think of in your head rather quickly. Okay, I'm not expecting really advanced or really high numbers here. Okay, so our first example is the square root of 9. Okay, so what number multiplied by itself, okay, twice would give you 9? In this case, I think 3 times 3. Okay, which means the square root of 9 is 3. For the square root of 16, what I think about with that is I automatically think of 4 times 4. Okay. Other ways you can think of it is you start to think, what two numbers, in this case it's a square root, can I combine together to create 16? Your first instinct might have been, okay, 2 times 8. Right? But that's not right, because these numbers have to be the same. We're talking about a root here. All right. So it has to be two of the same number. So I think, okay, what about 4 times 4? Right? And that works. 4 times 4, right, would give you 16. So the square root of 16 is 4. For item C, we have the third order root, or often called the cube root of 8. Okay? So that means you have 3 equal numbers multiplied together to give you 8. If I'm just stopping to think in my head, I know that 1 times 2 times 4 gives me 8, but they're not all the same number. Again, this is just, if you start thinking of it that way, it gets your mind turning into different scenarios that might give you that. In this case, I know that, oh, well, 2 times 2 is 4, and times 2 is 8. So that means the cube order root of this, because these are all the same number, must be 2. Now the fourth one, okay, item D here gets a little more difficult. It's a fourth order root. So you have 4 of the same number multiplied together. Now you can think about it the way I did and think of 4 numbers multiplied together to give you 81. Or I'm giving you examples that aren't going to be weird decimal places. Okay, so I can stop and think, well, let's try the same example from the last one. 2 times 2 times 2 times 2. Okay, it's the same number multiplied 4 times. But that is 16. Okay, so that doesn't work. What about 3? 3 times 3 times 3 times 3. Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. So that works, right? So that means the fourth order root of 81 must be 3. So you can stop and just try different iterations if you weren't using your calculator. I mean, obviously, in test scenarios when you are using radicals, you oftentimes would use a calculator, but this just helps you kind of visualize how these numbers work. Item E, the seventh order root of 1. Okay, well, we know if you're getting 1, it's just because you have a bunch of 1s multiplied by each other, right? So this means that the seventh order root of 1 is 1, and that's going to be the case for all the roots of 1. Okay, it's always just going to be 1. For item F, we have the negative root of the square root of 9? Well, we've already done the square root of 9 is 3. So the square root of 9 is 3. But remember, this negative is sitting here before it. So that's the same as negative 1 times the square root of 9. Well, we know from our first example the square root of 9 is 3. So we have negative 1 times 3, which gives us negative 3 here. Okay? Now, in item G, it's different. The negative is within the root sign. So we have the cube root of negative 8. Well, we know what the cube root is of 8. It's 2. Okay? So my first instinct is to think, well, could this be negative 2? And if it is, that means it'd be negative 2 times negative 2 times negative 2. So negative 2 times negative 2 is positive 4. Times negative 2 is negative 8. So it works. So that means the cube root here must be negative 2. And for the last item, it's similar to example E. Any root of 0, okay, in this case is just going to be 0. Okay, this is the 10th order root. It doesn't matter if it's the 10th order, 7th order, 4th order, okay, it's just 0. Okay. So now that I've explained what a radical is, I want to give you some of these rules. So these rules, you'll notice, are similar to exponent rules, okay? Looking at adding or subtracting them or multiplying them together, okay? So one thing to keep in mind here in all of these examples is you remember when we had exponents. So let's say we had 2 squared times 2 cubed. We added those exponents together. So that was 2 to the exponent 2 plus 3, which equals 2 to the exponent 5. We did that because the base here was the same. And a similar rule applies for radicals, all right? The root has to be the same when you're multiplying, when you have them being divided by each other, or when you have them being added or subtracted. Okay, they have to be the same root, or you can't just add them together normally. So our first operation, okay, you've kind of seen, if you have something, a to the exponent n, and the root of it, it's the same order of root, okay, you're going to see that that's just a. So in other words, if you had the third order root of 2 to the exponent 3, okay, so the exponent and the root and the order of the root are the same. So in that case, that's just equal to 2. You're going to see why when I talk about fractional exponents, okay? The next rule here is if you have the square root of, or the nth root of a, n being any number, times the nth root of b, okay, remember, these order of roots have to be the same. Then you can combine them under one root sign and multiply them together to that same order of root. The example I have here, the cube root of 8 times the cube root of 2. So that's the same as the cube root of the two numbers under the root sign multiplied together. So 8 times 2, which gives you the cube root of 16. Okay? If you have two roots divided by each other, again, the same order of root, that's the same as just combining them under the root sign and dividing those numbers that were under the sign together. So if you have root 2 divided by root 3, okay, they have the same order, again, without a number listed. That's assuming that it's 2. That's the same as the square root of 2 divided by 3. I just took the numbers from under the root sign and divided them. Okay? Our last rules for adding and subtracting. Okay? So if we're adding two of them together or subtracting, and they have the exact same number under the sign, and they have the same order of the root, that's the same in this case as 2 times that. Okay, just adding them together. So, for example, if we had root 2 plus root 2, again, these are the same root, so it's the same as 2 times root 2. If you add 3 times the square root of 5 minus 2 times the square root of 5, again, the same number under the root sign, same order of the root, then we simply get just the root of 5, okay? Just subtracting those. So 3 minus 2 gives you just 1. Okay. So just to do a few examples, you'll notice that this will be a shorter lesson, but again, this is a slightly more complicated in terms of just visualizing radicals. So we're going to evaluate each one of these. Again, you can pause this, do them yourself, and then play it through if you want, but it's up to you. So we have the square root of 2 squared. So remember, there's no number here, so that's implied that it's 2. So remembering our rules, the order of the root and the exponent under of the number or the power under the root symbol is the same. So that's the same as just 2. In this case, the third order root of 8. Okay, we've already done that in the previous slide. That's just 2. So it didn't follow any rules. I just wanted to make sure that you were aware of that. Root 2 times root 4, okay, again, has the exact same root sign here, the exact same order of root. So we can write that as the square root of 2 times 4, which is root 8. Okay. Example D here, the cube root of 27 divided by the cube root of 3. And again, since the order of the roots are the same, that's the same as the cube root of 27 divided by 3. Or we can simplify this because that gives you an even number, the cube root of 9. Okay? Next example, the fourth order root of 15 plus 4 times the fourth order root of 15. Again, they have the same order of root, 4, and the same number under the root sign of 15. This one is the radicand, if you remember. So you can simply add them together. You have 1 of them here and 4 of them here. So that makes 5 times the fourth root of 15. Our last example, the cube root of 8 minus the square root of 9. So we can't add or subtract those, okay? The order of the root is not the same, and the number within the root is not the same, okay? So that just stays as the cube root of 8 minus the square root of 9, okay? So you cannot simplify those together. Okay, so now that we've talked about orders of roots, what I want to talk about is fractional exponents. So you often see these radical numbers with a root sign. And there's another way to write them that is, at least in my opinion, easier to visualize. Okay, so if you have a root, let's say the root of 2, that's the second order root. That's the same as taking the number underneath the root sign and raising it to the exponent 1 divided by whatever the order of the root is, in this case 1/2. If I change that and this was a third order root of 2, this would simply be 2 to the exponent 1 divided by 3. Okay, it's divided by the order of the root. So instead of having them with root signs, you can express them as powers, okay, with a base and an exponent. And I find showing them that way is a far simpler way to visualize. So this formula shows you the general term. Okay, if you have any number under the root sign a, and it's raised to some order of a root n, you can write it as a power, a to the exponent 1 divided by n being the power of, or the order of the root. So let's look at a few examples. 4 to the exponent 1 over 2 is equal to the square root of 4, okay? Because you can just write that, remember, using this formula. And the square root of 4 we know is 2. Example B, we have 27 to the exponent 1 over 3. Again, we can start with the root sign, and because the number here is 3, that means it's the third order root. And the number here is 27. Okay, so you take the base, and that's what goes under the root sign. So we've looked at a similar one in the previous example. I know that that is 3 times 3 times 3. Again, just thinking about that in my head. So the answer to that one would be 3. Now they're not always that clean, all right? If you look at 50 to the exponent 1 over 4, again, that's the same as writing 50 under the root sign. And in this case, it was 1 divided by 4, so that's the fourth order root. Now this one you would not be able to solve, okay, without using a calculator. And if you place that in your calculator, you would get something like 2.659. Okay, again with rounding. Building on this ability to change a root into an item with an exponent, remember in our last lesson we talked about negative exponents. And we said if you had some number to a negative exponent, it's the same as 1 divided by that same power to the positive exponent. And it's no different here. The same rule applies. So if we had, let's go back to an example, 27 to the exponent negative 1 over 3. Again, using this rule for negative exponents, that's the same as 1 divided by 27 to the positive exponent 1 over 3. Okay? And if you wanted to show that as a root, be 1 divided by the third root of 27. Okay, third order root. Okay, all of these are interchangeable. Okay, and this formula shows you it just in algebraic terms for a general case that applies to all these numbers. Okay, so looking at our first example here, we have 8 to the negative 1 over 3. Okay, so that is the same, all right, as 1 divided by 8 to the exponent positive 1 over 3, which we can write as 1 divided by the cube root of 8. Okay, again, converting from the fractional exponent here to a root, which the cube root of 8 is 2, so it's the same as writing 1 divided by 2. In our second example here, we have 243 to the exponent negative 1 over 5. So again, starting with the same method, that gives us 1 divided by 243, and that's to the positive exponent 1 over 5, which is equal to 1 divided by the fifth order root of 243. Again, the base goes under the root sign. The number in the denominator of this fraction is the order of the root here. Okay, I'll do that in a different color. Okay. Now in this case, I know what the fifth order root of 243 is. You could also do it using your calculator. That would give you 1 divided by 3. Okay. Okay, so our last item to talk about, okay, is in every example with a fractional exponent, you've always seen it written as 1 divided by whatever this order of the root is, n. But there will be instances where you have a root that's then raised to an exponent, and the same exponent rules apply. Okay, so if you have, as a general term, we have a to the exponent m divided by n, m being some number. That's the same as writing the nth order root of a raised to the exponent m. Okay, and the reason for that is if you want to see that simplified out, okay, this is the same as if we had a to the exponent m divided by n. Okay, that's the same as a to the exponent 1 over n times m, right? Because if you were to multiply those, you'd get m over n. And if you remember from our exponent rules, if you had a number like 2 squared raised to another exponent 3, you multiplied those two exponents together. So that became 2 to the exponent 2 times 3, or 2 to the exponent 6. So what you'll notice is that same thing is happening here. These two are multiplied together. So we can separate those. A to the exponent 1 over n, okay, remember 1 divided by a number, you can write that as nth order root of the exponent a, and then raise it to the exponent m. Okay, so it's the same formula that you see here. All right, that's just kind of how that formula was developed. And that same formula applies again for a negative exponent, okay? It just becomes 1 divided by this number here, right? Because you're changing that exponent to a positive one. So looking at a few examples, our first example, 16 to the exponent 3 over 4. That's the same as the fourth order root of 16. Again, taking the number in the denominator here, that's the order of the root, and the base of the exponent goes under the root sign. And then that's raised to the exponent 3, or in other words, the number in the denominator here, or in the numerator here, sorry, on the top. So if you were to calculate that out, you can get 8. But the more important piece here is understanding how to change that to look like this. Okay. In example B, there's only one extra step. This is a negative exponent, and we want it as a positive exponent. So that just means it's 1 divided by everything that's written there, 36 to the exponent positive 3 over 2. Again, we just changed the sign of the exponent. And now we can write this as a root, 1 divided by, okay, we start with 36, okay, that's under the root sign, okay, so that's the number, that's the base here. Then we take the number in the denominator here, the 2, okay, that's the order of the root. And then we take the number in the numerator, and that whole term then becomes cubed, okay. So we can simplify this. We know that what the square root of 36 is, it's just 6. So that equals 1 divided by 6 cubed. Okay, and if you calculate that out, you get 1 divided by 216. All right, so these are just more rules, and by learning all the rules of exponents in the first lesson, as well as how to manipulate these pieces, the radicals and the fractional exponents, it makes manipulating equations or factoring equations that much simpler. Okay, so these all do take some practice. And on that note, okay, I've given you a few practice questions from exercise 11.2. I encourage you to do them. And like I've kind of said through this lesson, I hope that while you watch this lesson, you were trying these examples yourself. Okay, so trying them yourself and then listening to my answers makes it far easier for you to understand them and apply them. So that's all I had for this lesson. Thanks, everybody.